Imagine holding a grain of sand, an infinitesimal speck within your palm. This tiny particle, often unnoticed, contains billions of atoms, an entire universe of its own at the quantum level. Now, stretch your mind beyond the familiar, past the blue marble we call home, and out into the inky blackness. Envision nebulae, star-forming regions so vast that light itself takes centuries to cross, painting the void with cosmic artistry. Everything you perceive as large is about to shrink into insignificance. The largest known structure in the observable universe spans a mind-boggling 10 billion light-years, a scale that redefines reality. Understanding these colossal cosmic structures isn't just an exercise in numbers, it's a profound journey into the very architecture of existence, challenging our intuition and reshaping our sense of place within the boundless cosmos. This exploration compels us to confront the sheer audacity of the universe and our own humble, yet extraordinary capacity to comprehend it. In this documentary, we will embark on an extraordinary voyage, beginning with the familiar confines of our solar system, then expanding outwards. We'll meticulously chart this incredible expansion of scale, comparing Earth to our Sun, before venturing to supergiant stars like the formidable UY Scuti. Our journey will then encompass the breathtaking nebulae, the spiraling majesty of galaxies, and culminate in an encounter with the most gargantuan structure ever detected, the Hercules-Corona Borealis Great Wall. At every step, we will constantly contextualize these giants against the familiar expanse of our own solar system, ensuring their true scale is felt. If you're ready to transcend the ordinary and witness the universe in its most awe-inspiring, mind-bending forms, then hit that like button, subscribe to Terran, and prepare for a journey to the absolute borders of imagination. Let's begin. We begin our journey not in the distant, exotic reaches of the cosmos, but in the most familiar cosmic neighbourhood imaginable, our own solar system. To truly grasp the colossal scale of the universe's largest objects, we must first establish a baseline, a cosmic yardstick against which all other immensities will be measured. Our home planet, Earth, is a vibrant blue marble, a cradle of life, measuring approximately 12,142 kilometres in diameter. It is a world we can circumnavigate conceptually in less than a day by air, a tangible, comprehensible sphere. Yet, even this familiar sphere holds secrets of scale. Orbiting our Earth is the Moon, a celestial companion roughly 1/4 Earth's size. While seemingly close, the average distance separating us from our lunar neighbour is a staggering 384,400 kilometres. To put this in perspective, you could fit every single planet in our solar system, from Mercury to Neptune, lined up side by side within that expanse with room left over. This initial jump from the surface of Earth to its nearest celestial body already hints at the vast emptiness that defines space, a prelude to the true immensity that awaits us. Our primary star, the Sun, dwarfs Earth in a way that truly challenges comprehension. With a diameter of approximately 1.39 million kilometres, the Sun is about 109 times wider than Earth. This isn't just a slight increase, it means that over 1.3 million Earths could be packed inside the Sun. Imagine our entire planet, with its oceans, continents and bustling cities, as a single marble dropped into a cavernous, incandescent sphere. The Sun accounts for a staggering 99.8% of the total mass of our entire solar system. Its gravitational dominance absolute, anchoring every planet, asteroid and comet in an intricate cosmic dance. It is the heart of our system, a furious fusion reactor radiating energy that sustains all life on Earth, a power plant of truly incomprehensible magnitude. The distance separating Earth from the Sun further expands our perception of scale. This average separation, known as 1 astronomical unit, or AU, measures approximately 150 million kilometres. Light, the fastest entity in the universe, takes a little over 8 minutes to travel this distance. If you were to embark on a journey from Earth to the Sun in a modern jet airliner, travelling at around 900 kilometres per hour, it would take you roughly 19 years to reach your destination. This vast, seemingly empty gulf, where only the occasional asteroid or space probe traverses, is a testament to the sheer isolation inherent in even our local stellar system. Venturing further outward, the gas giants of our solar system introduce new layers of scale. Jupiter, the largest planet, could swallow over 1/300 Earths, its swirling storms a world unto themselves. Saturn, with its majestic rings, is still nearly 10 times wider than Earth. Even the distant ice giants, Uranus and Neptune, are each about 4 times Earth's diameter. These planets orbit at distances measured in many astronomical units: Jupiter at 5 AU, Saturn at 9.5 AU, Uranus at 19 AU, and Neptune at a staggering 30 AU. At Neptune's orbit, sunlight is a mere faint glow, and a round-trip communication from Earth takes over 8 hours. Beyond the familiar planets lies the Kuiper Belt, a vast disk of icy bodies extending from about 30 to 50 AU from the Sun. This region, home to dwarf planets like Pluto, represents a cold, dark frontier, a deep freeze where remnants from the solar system's formation slowly drift. To cross this belt travelling at light speed would take several hours, underscoring the growing immensity of our cosmic home. Yet, even the Kuiper Belt is not the true boundary of our solar system. That distinction belongs to the Oort cloud, a theoretical spherical shell of trillions of icy planetesimals stretching from approximately 2000 AU to an astounding 100,000 AU from the Sun. This diffuse, icy halo, the true gravitational frontier of our star, is so vast that light itself would take nearly 2 years to traverse its full extent. To put that into human terms, if you were born on the inner edge of the Oort cloud, light from the Sun would not reach you until your 2nd birthday. At these distances, the Sun is merely a bright star in the sky, indistinguishable from countless others, its warmth and dominance a distant memory. This ethereal boundary truly defines our solar system, a realm extending almost a quarter of the way to the nearest star system, Alpha Centauri. So, when we speak of our solar system, we are not merely talking about the planets orbiting the Sun. We are encompassing a colossal sphere of gravitational influence, a bubble of celestial mechanics spanning light years, not just kilometres. This entire, mind-bogglingly vast expanse, from the fiery heart of our Sun to the icy distant whispers of the Oort cloud, now serves as our initial, fundamental point of reference. It is our home, our cosmic island, and the largest entity we will consider small as we prepare to confront the truly gargantuan structures that lie beyond. End of hook section. Having established our solar system as a vast yet comprehensible cosmic island, where even the outermost reaches of the Oort cloud measure a staggering 2 light-years across, we are now ready to venture beyond its familiar boundaries. Our next destination shifts from a planetary system to its stellar heart, then explodes into the realm of true stellar titans, the supergiant stars. These celestial behemoths are not merely larger versions of our Sun, they are entities so immense that they redefine our very concept of scale. Our Sun, the radiant anchor of our home system, is a G-type main sequence star, a yellow dwarf by cosmic standards, yet large enough to contain over 1 million Earths. Its formidable size is already difficult for the human mind to fully grasp, but in the vast celestial tapestry, our Sun is a mere ember compared to the raging infernos that are supergiant stars. These are stars in the final dramatic phases of their lives, having exhausted the hydrogen fuel in their cores and expanded exponentially, their outer layers swelling to gargantuan proportions. They are characterized by extreme luminosity, often hundreds of thousands of times brighter than our Sun, and relatively short lifespans, typically burning out in a few million years, a cosmic blink compared to our Sun's projected 10 billion year existence. To begin this ascent into stellar immensity, consider Sirius, the brightest star in our night sky. It's roughly twice the mass and diameter of our Sun, already a significant leap but still a star that would comfortably fit within the orbit of Mercury. Next, we turn to stars that truly begin to challenge our solar system's domain. Take Betelgeuse, the prominent red shoulder of Orion, a star so iconic it's often cited for its vastness. Estimates place its radius at around 700 to 1,000 times that of our Sun. If Betelgeuse were positioned at the centre of our solar system, its fiery photosphere would extend well past the orbit of Mars, potentially even engulfing Jupiter. Our entire inner solar system, the rocky planets of Mercury, Venus, Earth and Mars, along with the asteroid belt, would be swallowed whole within its bloated crimson embrace. Imagine the Earth, not orbiting the Sun. but deep within the turbulent plasma convection currents of Betelgeuse itself, a truly impossible scenario that nonetheless illustrates the staggering difference in scale. Another famous red supergiant, Antares, in the constellation Scorpius, is comparable in size, often estimated at around 700 to 800 solar radii. Like Betelgeuse, it would easily consume the orbits of the first 4 planets, its vastness a harbinger of even greater giants. But even these stellar giants pale in comparison to the undisputed monarch of stellar size, UY Scuti. Located thousands of light-years away in the constellation Scutum, UY Scuti is a red hypergiant, and by current estimates the largest known star in the universe by sheer physical volume. Its radius is not merely hundreds, but an astonishing 1,700 times that of our Sun, with some upper estimates pushing it closer to 900 solar radii. Let's truly anchor this immense scale to our familiar solar system. If UY Scuti were to replace our Sun at the centre of our planetary system, its sheer colossal bulk would extend far beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt effortlessly. Its gaseous, incandescent surface would reach out to, or even slightly beyond, the orbit of Saturn. Some models even suggest its pulsating outer atmosphere could reach Uranus's orbit, a distance of approximately 19 astronomical units, or almost 2.9 billion kilometers. Picture that. Earth, along with all the other inner planets and gas giants up to Saturn, would not merely be orbiting this star, they would be inside it, consumed by its vast, diffuse envelope. The very concept of orbit would be meaningless for our world within such a behemoth. To traverse the circumference of UY Scuti would involve a journey of truly astronomical proportions. If you were somehow able to fly around its equator at the speed of light, it would take you almost 7 hours to complete a single lap. Compare that to the 2 minutes it takes light to circumnavigate our own Sun, or the mere fraction of a second for Earth. If you were to travel around UY Scuti at the speed of a commercial jetliner, the journey would last an unfathomable 2.4 million years. This single star, though possessing a mass only about 7 to 10 times that of the Sun, has expanded to such an unbelievable degree that its volume is equivalent to roughly 5 billion suns. 5 billion of our solar anchors, each large enough for 1 million Earths, contained within the fuzzy boundaries of one single pulsating star. UY Scuti's incredible size is a consequence of its advanced evolutionary stage. As a highly massive star, it burned through its hydrogen fuel at an accelerated rate, far quicker than less massive stars. Once its core hydrogen was depleted, it began fusing heavier elements, causing its outer layers to swell dramatically, becoming cooler and redder, yet radiating energy at an astonishing rate. It shines with a luminosity nearly 340,000 times that of our Sun, a beacon of unimaginable power, yet due to its immense distance and the obscuring dust lanes in the Milky Way, it is not visible to the naked eye. Its existence was only confirmed through careful astronomical measurements, including its distance and temperature, allowing scientists to infer its true, incredible dimensions. UY Scuti is not alone in its hypergiant status. Other stars such as WOH G64, another red hypergiant in the Large Magellanic Cloud, are estimated to be around 1,500 times the Sun's radius. Canis Majoris, once considered the largest, has a radius of approximately 1,420 solar radii, still utterly dwarfing our entire inner solar system. These celestial leviathans are rare, short-lived phenomena, burning through their fuel at such a furious pace that they are destined to end their lives in spectacular supernova, scattering heavy elements formed in their cores back into the cosmos, elements that will eventually form new stars, planets, and perhaps even life. The study of these stellar titans provides invaluable insights into the extreme ends of stellar evolution. They are living laboratories for understanding mass loss, the physics of extremely extended atmospheres, and the complex processes that lead to the most energetic explosions in the universe. But for now, their primary lesson is one of scale. Our solar system, a realm of intricate orbits and immense distances, now serves as a minuscule building block, a mere speck, when placed against the unimaginable grandeur of a single supergiant star. The transition from the Sun, our own star, to UY Scuti is a jump of such magnitude that it pushes the very limits of our spatial comprehension, a humbling realization as we prepare to confront even grander cosmic structures. From the solitary grandeur of a supergiant star, a single, dominant entity, we now expand our canvas to embrace the cosmic masterpieces born from stellar life and death, the nebulae. These aren't merely clouds in space, they are vast, ethereal tapestries of gas and dust, fundamental architects of the cosmos, serving simultaneously as the universe's stellar nurseries and the grand mausoleums of expired suns. They are the interstitial breath of galaxies, regions where matter gathers in diffuse, often luminous splendour, awaiting the gravitational impetus to form new stars or displaying the explosive aftermath of those that have lived their lives. At their most fundamental, nebulae are immense interstellar clouds composed primarily of hydrogen and helium, laced with traces of heavier elements and microscopic dust grains. Their sheer scale, even for the smallest examples, immediately pushes past anything we've contemplated within our solar system. Consider a simple dark molecular cloud, a relatively modest precursor to star formation. Even these dense pockets of gas and dust, often spanning just a few light years, would utterly engulf our entire solar system, from the Sun to the outermost reaches of the Oort cloud. Our cosmic island, which itself stretches 2 light years end to end, would be but a tiny internal speck within such a cloud, lost in its cold, dark embrace. This is the starting point for nebula scale. Let's turn our gaze to the Orion Nebula, catalogued as M42, a familiar celestial landmark visible even to the naked eye as a fuzzy patch in the sword of Orion. This isn't just a picturesque cloud, it's one of the most active and well-studied stellar nurseries within our own Milky Way galaxy. The Orion Nebula stretches approximately 24 light-years across. To put that into perspective, our entire solar system, with its Oort cloud boundary, fits comfortably within a mere 1/12 of a single light-year. The Orion Nebula is so vast that if our Sun were at its centre, the entire Oort cloud would be swallowed countless times over within its expansive, glowing arms. Light, our ultimate cosmic messenger, would take 24 years to traverse from one edge of this nebula to the other, a journey that for our solar system would take less than 2 years to cross its gravitational sphere of influence. This shimmering cloud is a dynamic cauldron, a birthplace for thousands of new stars, its glowing gases energized by the intense ultraviolet radiation from hot, young stars embedded within its heart. These massive young stars sculpt the surrounding gas and dust, carving out intricate patterns and creating powerful stellar winds that push against the nebula's material, continually reshaping this grand cosmic artwork. Even more dramatically, within the Eagle Nebula, also known as M16, lie the iconic structures dubbed the Pillars of Creation. These towering formations of interstellar gas and dust are not just beautiful cosmic sculptures. They are dense pockets where new stars are actively forming, protected from the harsh radiation of nearby massive stars. Each of these majestic pillars stands several light-years tall. The tallest pillar alone stretches approximately 4 light-years from its base to its tip. Imagine that, a single finger of cosmic dust, where our entire solar system could be stacked end-to-end twice, and still not reach from one end to the other. If our Sun and its entire Oort cloud were placed at the base of one of these pillars, the tip would be twice the distance to Proxima Centauri, our nearest stellar neighbour. These pillars are simultaneously sites of creation and destruction. Their elegant forms are being slowly eroded by the intense radiation from surrounding massive stars, a testament to the dynamic, often violent, nature of star formation. Nebulae aren't solely nurseries, they're also the universe's grand cemeteries, marking the final explosive chapters of stellar lives. Consider the Crab Nebula, designated M1, a violent, expanding remnant of a supernova event witnessed by Chinese astronomers in 1054 CE. This spectacular cloud is approximately 11 light-years across. If Oort cloud were placed within the Crab Nebula, it would be a minuscule point in a vast chaotic explosion. The nebula is still expanding at speeds of around 1,500 kilometers per second, a velocity so immense that its edges move outward by more than 130 million kilometers each day. Our entire journey from Earth to the Sun would be covered in just a single day by the expanding shockwave of this stellar tomb. At its core lies a rapidly spinning neutron star, the dense, collapsed remnant of the original star, pulsing with energy and illuminating the expanding filaments of gas that were once its outer layers. Another stunning example of a stellar remnant is the Helix Nebula, or NGC 72293, often called the Eye of God due to its uncanny resemblance to a cosmic eye. This is a planetary nebula, a less violent but equally profound end state for Sun-like stars. When a star like our Sun reaches the end of its life, it sheds its outer layers into space, forming an expanding shell of glowing gas. The Helix Nebula spans about 2.5 light-years in diameter. While smaller than the Crab Nebula, it is still a vast expanse, nearly 1.25 times the diameter of our entire Oort cloud, dwarfing our solar system with its ethereal multicoloured wisps. The central white dwarf star, the glowing core of the progenitor star, heats the expelled gas, causing it to fluoresce in brilliant hues, a beautiful, albeit temporary, farewell. To truly appreciate the largest nebulae, we must look beyond our local neighbourhood. The Tarantula Nebula, or 30 Doradus, located in the nearby Large Magellanic Cloud, is not just large, it is the most active star-forming region in our entire local group of galaxies. This gargantuan nebula spans over 1,000 light-years across. To conceptualize this, imagine laying our solar system, Oort cloud to Oort cloud, 500 times side by side. That is the diameter of this single monstrous stellar factory. Within its turbulent depths, tens of thousands of massive stars are forming, their collective energy output so immense it would utterly overwhelm our Sun. The Tarantula Nebula is so luminous that if it were as close to us as the Orion Nebula, it would cast visible shadows on Earth at night. It is a region of violent creation, where massive stars live fast and die young, constantly enriching the surrounding gas with heavy elements through their supernovae, preparing the ground for future generations of stars and eventually planets. Closer to home, within our own Milky Way, the Carina Nebula, NGC 3372, offers another spectacular display of colossal scale. This nebula stretches over 300 light-years in diameter, more than 150 times the diameter of our solar system's gravitational reach. It is home to some of the most massive and luminous stars known, including Eta Carinae, a hypergiant whose eruptions have shaped the nebula's intricate structures. The Carina Nebula is a testament to the power of stellar winds and radiation, constantly carving out pillars, cavities, and dark lanes within its vast expanse, a dynamic interplay of creation and sculpting on a truly galactic scale. These individual nebulae, as immense as they are often merely bright knots within even larger structures. The giant molecular clouds, the Orion Molecular Cloud Complex for instance, which contains the Orion Nebula, stretches hundreds of light-years across, a vast, cold reservoir of molecular hydrogen gas where star formation is not just happening, but is a systemic galaxy-wide process. These complexes can span up to 1,500 light-years, representing the largest known individual objects of gas and dust. They are the primary building blocks for entire spiral arms of galaxies, containing enough raw material to form millions of stars like our Sun. Our entire solar system, from its fiery heart to its icy fringes, is merely a dust mote within the galactic disk, a disk that is itself woven from these colossal star-birthing clouds. The sheer scale of these nebulae, from the relatively modest planetary nebulae to the gargantuan molecular cloud complexes, underscores a critical point. The universe operates on scales that consistently defy human intuition. We've moved from contemplating a single star that swallows our solar system to gas clouds so vast they could contain hundreds of our solar systems. Each light-year of their expanse marking a distance light itself takes a year to cross. These cosmic canvases are not merely beautiful, they are fundamental dynamic factories where the raw materials of the universe are recycled, forged, and given new life, forever expanding our understanding of what constitutes a truly enormous object. If nebulae were the intricate brushstrokes of cosmic art, then galaxies are the colossal canvases themselves, each an island universe teeming with billions upon billions of stars, nebulae, planets, and the mysterious dark matter that binds it all together. From the relatively confined, albeit vast expanses of stellar nurseries and supernova remnants, we now make a quantum leap to structures that define the very fabric of the cosmos on a truly monumental scale. Our own home, the Milky Way galaxy, serves as our guide into this new dimension of immensity. Our Milky Way, a majestic spiral galaxy, typically conjures images of a sprawling luminous disk when seen from afar. Yet, its true dimensions and complexity are profoundly difficult to grasp from our vantage point within one of its spiral arms. To understand the scale of our galaxy is to appreciate that every star you've ever seen with the naked eye, save for a handful of nearby galaxies like Andromeda, is merely a part of our local galactic neighbourhood. The visible, luminous disk of the Milky Way spans an astonishing 100,000 light-years in diameter. To put this in staggering perspective, remember our fringes of the Oort cloud measures approximately 2 light-years across. This means you could line up an incredible 50,000 entire solar systems, end to end, just to traverse the visible diameter of our galaxy. Light, the fastest entity known, takes a full 100,000 years to travel from one side of the galactic disk to the other. Our human history, stretching back a mere few millennia, is but an ephemeral blink in the face of such a journey. Even a supergiant star like UY Scuti, which we previously marvelled at for its ability to engulf the orbit of Saturn, becomes an infinitesimally small point, less than 100,000th of a light-year in diameter, within this galactic expanse. The disk itself is not uniformly thick. It thins out from a central bulge, but on average, it's about 1,000 light-years thick. So, while our solar system is just a 2 light-year wide bubble, the galaxy's disk is 500 times thicker than our entire system's diameter. Our Sun, along with its retinue of planets, orbits approximately 27,000 light-years from the galactic centre, nestled within one of the Milky Way's spiral arms, specifically the Orion arm, or local arm. This means our Sun travels at an astounding speed of about 220 km per second around the galactic core, completing one full revolution roughly every 220 to 250 million years. In that colossal span of time, known as a cosmic year, life on Earth has evolved from simple organisms to complex ecosystems, dinosaurs rose and fell, and humanity emerged. Yet, the Sun has only completed about 20 such orbits since its birth, a humbling testament to the galaxy's vastness and the slow march of cosmic time. At the very heart of the Milky Way lies a dense spheroidal region known as the galactic bulge, stretching roughly 10,000 light-years across. This central region is a crowded metropolis of ancient stars, gas and dust, a population far denser than in the spiral arms. Within its innermost 200 light-years resides Sagittarius A, a supermassive black hole with a mass equivalent to over 4 million suns. While its event horizon is comparatively tiny, only about 24 million kilometers in diameter, a mere 17 times the diameter of our Sun, which itself is less than 1/10,000th of a light-year. Its gravitational influence governs the motions of stars and gas throughout the entire central region of the galaxy. This immense black hole, a gravitational anchor of staggering proportions, could swallow hundreds of millions of Earths and still be considered small compared to the scale of the galaxy it dominates. However, the true gravitational and physical extent of our Milky Way stretches far beyond its luminous disk and central bulge. Our galaxy is enveloped by an immense, nearly spherical halo of dark matter. This invisible shroud, detectable only through its gravitational effects on the visible matter, is estimated to extend for at least 300,000 light-years in diameter, with some models suggesting it could be as large as 500,000 light-years. If our solar system measures 2 light-years across at its widest, then this dark matter halo, the true boundary of our galaxy's gravitational dominion, is an astonishing 150,000 to 250,000 times wider. Our entire solar system, with its vast Oort cloud, is nothing more than an almost imperceptible speck within this colossal unseen sphere of influence. Scattered throughout this vast dark matter halo are hundreds of ancient stellar systems known as globular clusters. These spherical collections of hundreds of thousands to millions of stars orbit the galactic centre at great distances, sometimes as far as 150,000 light-years away from the core, providing further evidence of the Milky Way's immense gravitational reach. These clusters, each a miniature galaxy of its own, are themselves thousands of light-years away from our Sun, underscoring the incredible distances within our own galaxy. The Milky Way is not just vast in size, but in content. It is estimated to contain between 100 billion and 400 billion stars, each potentially the centre of its own planetary system. This means there could be hundreds of billions of solar systems like our own, each a cosmic island of planets, orbiting within this single galactic structure. The total mass of our Milky Way, when factoring in the pervasive dark matter, is estimated to be around 1.5 trillion times the mass of our Sun. To conceptualize this, imagine 1.5 trillion suns, each a million times the size of Earth, spread across an area 50,000 times wider than our entire solar system. The sheer immensity of the Milky Way truly humbles our previous scales. We have moved from a colossal supergiant star to an entire universe of stars, gas, and dark matter, gravitationally bound across hundreds of thousands of light years. Our solar system, once our largest reference point, is now reduced to a microscopic mote of dust, lost within a single spiral arm of this magnificent cosmic titan. And yet, even this galactic marvel is merely a constituent part of an even grander hierarchy of structures, a stepping stone on our journey to the absolute largest objects in the universe. Having grasped the staggering scale of our Milky Way, a vast island of stars stretching across 100,000 light years, we must now confront the realization that even this magnificent galaxy is not an isolated entity. Instead, it is merely one component within an even grander cosmic tapestry, gravitationally tethered to its neighbours, forming intricate celestial communities known as galaxy groups and clusters. These structures represent the next monumental leap in our journey, revealing that matter in the universe organises itself into ever larger, more complex hierarchies. Our immediate galactic neighbourhood is a modest collection called the local group. This cosmic archipelago, held together by the mutual gravitational attraction of its members, spans an immense region approximately 10 million light-years in diameter. Within this colossal sphere of influence reside over 80 galaxies, ranging from the two dominant spirals, our own Milky Way and the colossal Andromeda Galaxy, to numerous smaller dwarf galaxies like the Triangulum Galaxy and the Magellanic Clouds, which are satellite galaxies to the Milky Way. To truly appreciate this scale, recall that distant Oort cloud measures a mere 2 light-years across. The local group, therefore, is 5 million times wider than our entire solar system. If our Milky Way itself, 100,000 light-years wide, were to be laid end to end, you could fit 100 such galaxies across the local group's diameter. This is the scale of our immediate cosmic family, a collection of galactic islands slowly, inexorably falling toward one another. The most dramatic interaction within the local group is the impending collision between the Milky Way and Andromeda. These two spiral titans, the gravitational anchors of our group, are currently hurtling towards each other at a breathtaking speed of approximately 110 kilometers per second. In roughly 4.5 billion years, their majestic disks will begin to merge, a slow balletic collision that will eventually forge a new colossal elliptical galaxy, sometimes whimsically dubbed Milkomeda. This future event, though billions of years away, underscores the dynamic, gravitationally driven evolution that governs structures even on the scale of galaxy groups. The vast empty space between these galaxies is not truly empty. It is a battleground of unseen gravitational forces, pulling and shaping the destiny of entire stellar populations. Stepping beyond the local group, we encounter even more spectacular aggregations, galaxy clusters. These are the universe's true cities of galaxies, often containing hundreds, even thousands, of individual galaxies, all bound together by gravity into a single cohesive unit. The sheer mass within these clusters is truly mind-boggling, reaching quadrillions of times the mass of our Sun. The distances involved are equally formidable. The closest significant galaxy cluster to our local group is the Virgo cluster, located approximately 54 million light-years away. It sits at the heart of the larger Laniakea supercluster, which we are a part of. The Virgo cluster itself spans a region roughly 15 million light-years across. Compare this to our solar system, which is only 2 light-years wide. The Virgo cluster is 7.5. You were to place our entire local group 10 million light-years wide into the Virgo cluster, it would barely fill a portion of its colossal extent. The Virgo cluster contains over 2,000 galaxies, dominated by 3 giant elliptical galaxies, Messier 87, Messier 86, and Messier 49, each a super heavyweight champion of the cosmic ring. Within these dense galactic metropolises, the environment is dramatically different from the serene isolation of a void or even the relatively tranquil outskirts of a galaxy group. The space between galaxies in a cluster is not empty vacuum, but filled with an extremely hot, diffuse plasma known as the intracluster medium. This gas, heated to millions of degrees Celsius by the violent gravitational collapse of the cluster and by powerful supernovae, emits intense X-rays, making galaxy clusters some of the brightest X-ray sources in the sky. This hot gas, though tenuous, represents a significant fraction of the cluster's total baryonic, normal matter, often outweighing the combined mass of all the stars in all the galaxies. Gravitational lensing, a stunning prediction of Einstein's theory of general relativity, is a common phenomenon in galaxy clusters. The immense mass of a cluster, particularly its dark matter halo, warps the fabric of space-time, bending the light from more distant background galaxies. This creates distorted, magnified, and sometimes multiple images of these faraway galaxies, acting like cosmic funhouse mirrors. This phenomenon is not only visually spectacular, but also serves as a powerful tool for astronomers, allowing them to map the distribution of dark matter within the cluster, revealing that the invisible, mysterious substance accounts for upwards of 80% of a cluster's total mass. The dark matter halo of a cluster can extend for tens of millions of light years, making it the true gravitational backbone of these structures, far larger than the visible galaxies they contain. The dynamics within galaxy clusters are a constant slow-motion ballet of destruction and creation. Galaxies do not simply orbit peacefully, they frequently interact, sometimes merging, sometimes suffering from galactic cannibalism, where larger galaxies absorb smaller ones. Tidal forces from the cluster's overall gravitational field can strip gas and even stars from individual galaxies, transforming star-forming spiral galaxies into quiescent elliptical galaxies, devoid of fresh star-making material. This process, known as ram pressure stripping, is a powerful evolutionary mechanism, sweeping away the cold gas needed for star formation as galaxies plunge through the hot intracluster medium. The central dominant elliptical galaxies and clusters often grow to monstrous sizes, accumulating mass from countless smaller galaxies over billions of years, becoming the true giants of these galactic cities. These galaxy clusters, with their thousands of members and quadrillions of solar masses, represent the largest structures in the universe that are genuinely gravitationally bound. Their sheer scale is almost beyond comprehension. Our tiny solar system, previously a colossal 2 light-years wide, now resides in a galaxy that is a mere 100,000th the diameter of a typical galaxy cluster. We have traversed from the familiar comfort of our Earth to the breathtaking immensity of a single supergiant star, then to nebulae vast enough to contain hundreds of solar systems, and now to entire island universes, the Milky Way, which are themselves mere specks within gravitationally bound communities that stretch for tens of millions of light years. The universe, we are learning, is a place of hierarchical grandeur, each layer of organisation vastly overshadowing the one before it. We have journeyed from the minuscule blue marble of Earth to the solar titan that anchors our system, then outwards to supergiant stars, and finally across the immense sprawl of galaxies and the bustling cities of galaxy clusters. Yet, even these colossal aggregations are not isolated cosmic islands. They are in fact interconnected nodes within an even grander, more breathtaking architecture that defines the universe at its largest observable scales, the cosmic web. This intricate foam-like structure is the universe's true skeleton, a vast network of filaments and walls of galaxies, interspersed with enormous sprawling regions of near-total emptiness known as cosmic voids. Imagine the universe not as a uniformly distributed cosmic soup, but as a colossal, three-dimensional sponge. The dense, luminous parts of that sponge are where matter has concentrated, forming the filaments and walls. The vast cavernous holes in the sponge are the voids. This complex interconnected pattern is not merely a theoretical construct, it is directly observed through sophisticated galaxy surveys that map the positions of millions of galaxies across billions of light years. These surveys, like the Sloan Digital Sky Survey, have transformed our understanding, revealing a universe structured on scales that truly defy our terrestrial intuition. The filaments are the thread-like structures of the cosmic web. giant tendrils of matter that stretch for hundreds of millions of light years. These aren't just random lines of galaxies, they're gravitational highways where galaxy groups and clusters gather, drawn together by the pervasive pull of gravity. Our own local group, containing the Milky Way and Andromeda, is part of such a filament, which itself flows into the larger Laniakea supercluster. A typical filament can span anywhere from 50 million to 300 million light-years in length, sometimes even longer. To place this into context, extending 2 light-years would need to be laid end-to-end 25 million times just to cross a filament 50 million light-years long. Our Milky Way galaxy, 100,000 light-years in diameter, would be but a single pearl on a string, with hundreds, even thousands, of similar galaxies stretching away into the cosmic distance along these vast cosmic roadways. These filaments converge at nodes, which are the sites of the densest galaxy clusters, the gravitational anchors of the cosmic web. Here, hundreds or even thousands of galaxies are packed together, along with vast quantities of hot X-ray emitting gas and unseen dark matter, forming massive gravitational wells. These nodes are the cosmic urban centres, bustling with galactic activity and dense concentrations of baryonic and dark matter. The gravitational pull from these concentrated nodes continuously draws in more galaxies from the surrounding filaments, causing the web to slowly grow and evolve over cosmic time. Conversely, the cosmic voids are the antithesis of these dense filaments. These are colossal, largely empty regions that make up the vast majority of the universe's volume, estimated to be around 90%. Voids are not entirely empty, but their density of galaxies and matter is significantly lower than the cosmic average, often just 10% to 20% of the density found in the filaments. A typical void can span hundreds of millions of light-years across. Some of the largest known, like the Eridanus supervoid or the KBC void, which our galaxy resides near the edge of, can stretch over 1 billion light-years in diameter. To grasp the emptiness, imagine our solar system, a 2 light-year expanse, existing within a void 1 billion light-years across. It would be akin to a single dust particle within a hollow sphere with a diameter equivalent to half the distance between Earth and the Sun. If you could travel through a void, you would fly for millions of years at the speed of the light, encountering perhaps a few lonely dwarf galaxies separated by truly unfathomable distances, their stars mere pinpricks in an otherwise featureless blackness. The isolation within a void would be absolute, a profound sense of cosmic solitude. The formation of this intricate cosmic web traces its origins back to the universe's infancy, immediately following the Big Bang. During an unimaginably brief period called inflation, tiny quantum fluctuations in the primordial plasma were stretched to cosmic scales. These minuscule variations in density, perhaps 1 part in 100,000, became the seeds of all large-scale structure. Regions that were infinitesimally denser began to gravitationally attract more matter, slowly growing over hundreds of millions of years. Conversely, regions that were slightly less dense began to lose matter to their denser neighbours, becoming progressively emptier. This process, known as gravitational instability, amplified the initial subtle ripples into the grand architecture we observe today. The cosmic web is, in essence, gravity's artwork, sculpted over 13.8 billion years. This realization fundamentally shifts our perspective. For centuries, our models of the universe often assumed a relatively smooth and uniform distribution of matter. But the cosmic web paints a much more dynamic, lumpy picture. It dictates where galaxies can form, where clusters can thrive, and where vast stretches of the universe remain barren. Our own Milky Way, an island of 100 billion stars and 100,000 light-years in diameter, is but a minor component in one of these immense filaments, caught in a delicate balance between the outward push of cosmic expansion and the inward pull of surrounding gravitational wells. The discovery and mapping of the cosmic web is a triumph of modern astronomy, transforming our understanding of the universe from a simple, expanding volume into a dynamic, interconnected network of incredible scale. It forces us to acknowledge that the largest objects in the universe are not single stars or even individual galaxies, but these vast, gravitationally organized structures that span truly mind-boggling distances, making our entire solar system an utterly insignificant yet perfectly placed observation point within this grand cosmic design. Our cosmic voyage has ascended from the familiar embrace of our solar system, past the colossal supergiant stars, through the breathtaking artistry of nebulae, and across the intricate star-studded expanse of individual galaxies. We then discovered that these island universes are themselves gathered into bustling galactic cities, the galaxy groups and clusters, but the universe's architectural genius doesn't stop there. These clusters, these massive concentrations of matter, are not randomly scattered. They are part of an even grander assembly, forming the very apex of gravitationally influenced structures below the largest coherent patterns of the cosmic web, the superclusters. Superclusters are truly the cities of galactic cities, vast collections of galaxy groups and clusters, all loosely associated and flowing together under the influence of immense gravitational gradients. Unlike galaxy clusters, which are truly gravitationally bound, superclusters are so enormous that the expansion of the universe often works against their complete gravitational collapse. Instead, they represent regions of the cosmic web where the density of matter is significantly higher than average, causing a collective, coherent motion of galaxies within them. They are like vast cosmic watersheds, where matter slowly, inexorably, flows downhill towards the deepest gravitational valleys. Our own Milky Way galaxy, that magnificent spiral spanning 100,000 light-years, is not just a member of the local group. It is a tiny component of the Laniakea supercluster. Discovered in 2014 by a team led by Brent Tully, Laniakea, a Hawaiian word meaning immeasurable heaven, is a fitting name for a structure of such staggering proportions. This supercluster is a colossal entity, stretching an astounding 520 million light-years across. To grasp this scale, remember our solar system, encompassing its 2 light-year wide Oort cloud. Laniakea is 260, our galactic home. Were to be placed end to end, you would need to line up approximately 5,200 such galaxies to span the width of Laniakea. This single supercluster contains roughly 100,000 galaxies, collectively amounting to a mass equivalent to 100 quadrillion suns, or 1017 solar masses. The defining characteristic of Laniakea, and indeed all superclusters, is not merely their size or galaxy count, but the synchronized flow of galaxies within them. Using sophisticated techniques to map the peculiar velocities of thousands of galaxies, their motions relative to the overall expansion of the universe, astronomers uncovered a vast interconnected network of streams, all converging towards a central gravitational anomaly. This massive diffuse concentration of matter, located approximately 250 million light-years away in the direction of the Norma cluster, is known simply as the Great Attractor. It's not a single object, but a region of space with an unusually high density of matter, pulling on everything within Laniakea. Our own Milky Way is not stationary in this cosmic flow. It is hurtling towards the Great Attractor at an incredible speed of approximately 600 kilometers per second, or over 1.3 million miles per hour. This is a journey that will take billions of years, a testament to the patient, inexorable power of gravity operating on truly cosmic scales. Beyond our local Laniakea, the universe reveals an astonishing array of other superclusters, each a testament to the universe's grand design. Consider the Perseus-Pisces supercluster, located about 250 million light-years from us. This immense structure forms a prominent chain of galaxy clusters stretching for over 250 million light-years. Within its length, you could fit 125 million solar systems laid end to end. It is one of the most massive structures in the northern celestial hemisphere, a truly colossal cosmic river of galaxies flowing through space. This supercluster stands out because of its elongated filamentary shape, a clear example of the dense walls within the cosmic web. Further out, the Coma supercluster, approximately 300 million light-years away, presents another awe-inspiring example. This supercluster, centered on the rich Coma cluster and Leo A cluster, is a dense concentration of hundreds of galaxy clusters, forming a region of enhanced galaxy density that spans hundreds of millions of light-years. While its exact boundaries are hard to define due to its diffuse nature, its gravitational influence extends over an enormous volume. Imagine a region of space where our solar system would be just a tiny speck, and within which hundreds of galaxy clusters, each containing thousands of galaxies, are all jostling and interacting. These superclusters, though they are the largest structures defined by coherent gravitational flows, are not themselves gravitationally bound in the same definitive way as a planet orbiting a star or even galaxies within a cluster. The universe's accelerated expansion, driven by dark energy, works to pull these immense structures apart. However, the overdensity of matter within a supercluster is significant enough that it still exerts a dominant gravitational pull on its constituent galaxies and clusters, causing them to move together like water swirling towards a drain. Even as the drain itself is expanding, the very existence and intricate dynamics of superclusters provide crucial data for cosmologists. They are living laboratories for understanding how gravity shapes the universe on the larger scales, how dark matter distributes itself, and how the interplay between gravity and dark energy dictates the evolution of cosmic structure. The study of these vast megastructures helps us refine our cosmological models, allowing us to trace the universe's history back to the tiny fluctuations of the early cosmos that eventually grew into these breathtaking arrangements. The sheer scale is profound. We began with our solar system, a 2 light-year wide expanse. We then considered a galaxy, our Milky Way, 100,000 light-years across. Now we're talking about superclusters, structures that encompass tens to hundreds of galaxy clusters, sprawling across hundreds of millions of light-years. Laniakea alone is 5 to 300 times the diameter of our entire galaxy. This means our solar system is not merely a tiny speck within a galaxy, but a truly microscopic, almost inconsequential point within a cosmic river that dwarfs even the grandest of galaxies. This relentless expansion of scale pushes the boundaries of human imagination, constantly redefining what we consider to be truly enormous in the universe. We have traversed the hierarchy of cosmic structures, from the intimate scale of our solar system to the mind-bending dimensions of superclusters like Laniakea, a vast river of galaxies flowing across 520 million light-years. But how do we, inhabitants of a relatively small planet within one of billions of galaxies, measure these truly astronomical distances and comprehend such colossal objects? How do we map the universe's grand architecture, extending billions of light-years into the cosmic abyss? The answer lies in the ingenious methods of cosmic cartography, a complex distance ladder built on fundamental physics, telescopic ingenuity, and the relentless pursuit of precision. At the base of this ladder are the direct measurements within our own solar system, using radar ranging to determine planetary distances with incredible accuracy. However, these methods are effective only for relatively nearby objects. To measure the distances to stars within our galaxy, astronomers employ parallax, the apparent shift in a star's position as Earth orbits the Sun. Imagine holding your finger out and closing one eye, then the other. Your finger appears to jump. Stars do the same against the backdrop of more distant stars. The larger the shift, the closer the star. Missions like ESA's Gaia satellite have measured the parallax for over 1 billion stars in our Milky Way, providing a precise 3D map of our galactic neighbourhood. But even this powerful technique is limited to distances of a few tens of thousands of light-years, barely encompassing a fraction of our galaxy's diameter. To reach beyond, to measure the distances to other galaxies and the structures they inhabit, astronomers rely on standard candles, objects with a known intrinsic brightness. If you know how bright an object truly is, and you measure how bright it appears from Earth, you can calculate its distance. One crucial type of standard candle is the Cepheid variable star. These pulsating stars brighten and dim in a predictable cycle, and critically, their period of pulsation is directly related to their intrinsic luminosity. Henrietta Swan Leavitt discovered this period luminosity relationship in the early 20th century. By observing a Cepheid in a distant galaxy, measuring its pulsation period, astronomers can deduce its true brightness. Comparing this to its apparent brightness yields its distance. This method allowed Edwin Hubble to prove in the 1920s that spiral nebulae were in fact separate galaxies, millions of light-years beyond our Milky Way. A Cepheid variable, however, can typically be observed only out to about 100 million light-years, which is a mere fraction of the diameter of a supercluster like Laniakea. Even for our solar system, which spans 2 light-years, a Cepheid would have to be observed from 50 million solar systems away if they were lined up. For even greater distances, astronomers turn to another far more luminous standard candle, type Ia supernovae. These are cataclysmic explosions of white dwarf stars in binary systems. When a white dwarf accumulates enough mass from its companion star, it reaches a critical limit, the Chandrasekhar limit, and detonates with a consistent, predictable peak luminosity. Because these explosions are so incredibly bright, outshining an entire galaxy for a short period, they can be seen across billions of light years. By measuring the apparent brightness of a type Ia supernova, scientists can calculate the vast distances to the host galaxy, pushing our cosmic reach much further. This method was instrumental in the discovery of dark energy and the accelerating expansion of the universe. Imagine observing a star exploding in a galaxy so distant that the light has travelled for billions of years to reach our telescopes, traversing a distance 1 billion times the diameter of our solar system. Yet, even standard candles have their limits and inherent uncertainties. For truly mapping the largest structures, the cosmic web, and the superclusters that comprise it, astronomers primarily rely on redshift and Hubble's law. As the universe expands, the light from distant galaxies is stretched to longer, redder wavelengths, a phenomenon known as cosmological redshift. This is analogous to the Doppler effect, where the pitch of a siren drops as an ambulance moves away from you. The greater the redshift, the faster the galaxy is receding from us, and thus, the farther away it is. Edwin Hubble famously quantified this relationship in 1929, establishing what is now known as Hubble's law. The recessional velocity of a galaxy is directly proportional to its distance. To apply this, astronomers use powerful spectrographs to analyze the light from galaxies, identifying spectral lines, unique fingerprints of elements like hydrogen and helium, and measuring how much these lines have shifted towards the red end of the spectrum. This tells us the galaxy's recessional velocity. Then, using Hubble's law, we can infer its distance. This technique allows us to probe the universe across truly gargantuan scales. Mapping galaxies out to the very edge of the observable cosmos, billions of light years away. For instance, to map the Hercules-Corona Borealis Great Wall, a structure spanning 10 billion light years, redshift measurements are the only viable tool. To contextualize this, a distance of 1 billion light years is 500 million times the diameter of our entire solar system. Measuring such a redshift allows us to place objects at distances truly unimaginable to the human mind, enabling us to piece together the large-scale structure of the universe. However, redshift alone isn't perfect for local distances, as galaxies also have peculiar velocities, motions due to local gravitational pulls, like our Milky Way's journey towards the Great Attractor. These local motions can distort the redshift signal, making it appear as though a galaxy is closer or farther than it truly is based solely on cosmic expansion. To refine these measurements, particularly for mapping superclusters and understanding their internal dynamics, astronomers employ a sophisticated technique called baryon acoustic oscillations, or BAO are essentially frozen sound waves from the early universe. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma where matter and radiation were tightly coupled. Pressure waves, like sound waves, rippled through this plasma, pushing matter outwards from denser regions. When the universe cooled sufficiently for neutral atoms to form, matter and radiation decoupled, and these sound waves effectively froze, leaving an imprint on the distribution of matter. This imprint manifests as a characteristic scale in the clustering of galaxies today. Galaxies are slightly more likely to be found at a certain preferred separation, roughly 490 million light-years, which is the distance those sound waves travelled before freezing. This scale acts as a standard ruler in the cosmos. By meticulously surveying the positions of millions of galaxies, astronomers can detect this subtle BAO signal. By measuring the apparent size of this standard ruler at different distances, they can determine how much the universe has expanded over that time, providing an incredibly precise measure of cosmic distances and the expansion history of the universe. This technique is like placing identical, cosmic-sized meter sticks across billions of light-years and measuring how large they appear to us. The BAO scale, spanning 490 million light-years, is 245 million times larger than our solar system's Oort cloud. Mapping these oscillations allows us to create detailed 3D maps of the cosmic web, revealing the filaments, nodes, and voids with unprecedented accuracy, enabling the identification of structures like superclusters and even larger formations. Finally, gravitational lensing also serves as a critical tool in cosmic cartography, especially for understanding the distribution of dark matter within large structures. The bending of light from distant galaxies by foreground galaxy clusters allows astronomers to infer the total mass of the clusters, including their invisible dark matter halos which can. This method confirms the existence of these enormous, unseen gravitational anchors that govern the formation and evolution of superclusters. The combination of these techniques, from direct radar ranging and stellar parallax to standard candles, redshift, baryon acoustic oscillations and gravitational lensing, allows astronomers to build a comprehensive, multi-layered map of the universe. Each rung on this cosmic distance ladder allows us to peer further into the abyss, revealing the true, mind-boggling scale of the largest objects. Without these sophisticated tools, the vast superclusters, the intricate cosmic web, and the truly monumental structures we are about to encounter would remain entirely hidden, their immense existence forever beyond our grasp. Our journey through the cosmos has relentlessly pushed the boundaries of human comprehension. From the familiar comfort of Earth to the sun-swallowing immensity of Scudi, then across nebulae vast enough to cradle countless solar systems, and finally encompassing entire galaxies and their sprawling supercluster cities, each step has recalibrated our cosmic yardstick, reducing the previously colossal to mere specks. Yet, as we approach the farthest reaches of our observable universe, a singular, almost mythological structure emerges, so unbelievably vast that it dwarfs everything we have discussed thus far, challenging the very principles upon which modern cosmology is built. This is the Hercules-Corona Borealis Great Wall, the largest known object in the universe. Discovered in 2013 by a team of Hungarian and American astronomers analysing the distribution of gamma-ray bursts, the Hercules-Corona Borealis Great Wall, often abbreviated as the Hercules-Corona Borealis GRB Wall, is not a solid, singular object in the traditional sense, but a colossal filamentary structure, an immense concentration of galaxies, galaxy clusters, and superclusters. Its very name, evocative of ancient myths and astronomical constellations, hints at its extraordinary nature, spanning the directions of Hercules and Corona Borealis in the northern celestial hemisphere. To fully grasp the scale of this cosmic leviathan, we must again turn to comparison, allowing our solar system to serve as our humble, ever-shrinking benchmark, measures approximately 2 light-years across. The Hercules-Corona Borealis Great Wall stretches an incomprehensible 10 billion light-years in its longest dimension. This means you would need to line up our entire solar system, end to end, an astounding 5 billion times just to traverse this single, immense structure. Let's ascend the ladder of scale once more. A supergiant star like Scudi, which could swallow the orbit of Saturn, measures a minuscule fraction of a light-year, a cosmic dust motes when placed against this wall. Our Milky Way galaxy, an island of 100 billion stars spanning dwarfed by the Great Wall by a factor of 100,000 talons. Imagine 100,000 Milky Ways, stacked side by side just to span this single cosmic feature. Even our local group of galaxies, a collection of over 80 galaxies stretching 10 million light-years across, is 1,000 times smaller than this immense structure, and the Laniakea supercluster, our own galactic continent measuring 520 million light-years, appears as a mere building block. For the Hercules-Corona Borealis Great Wall is nearly 20 times wider than Laniakea. But perhaps the most shocking comparison of all is its relation to the observable universe itself. The estimated diameter of the entire observable universe is approximately 93 billion light-years. The Hercules-Corona Borealis Great Wall, at 10 billion light-years across, spans roughly 1/9, or over 10%, of this entire cosmic canvas. Imagine looking at a map of Earth and finding a single mountain range that covers more than 10% of the planet's surface. This is the astronomical equivalent of what we're observing. It is a structure so vast that it truly pushes the boundaries of what our current cosmological models predict should exist. The discovery of this Great Wall was not a direct visual observation in the way one might photograph a galaxy. Instead, it emerged from painstaking analysis of gamma-ray bursts, GRBs. These incredibly energetic explosions, resulting from the collapse of massive stars or the merger of neutron stars, are the most luminous events in the universe. They are so bright that they can be detected from billions of light years away, effectively acting as cosmic beacons, illuminating the distribution of matter in the distant universe. By mapping the locations of these GRBs, which are typically associated with star-forming regions within galaxies, astronomers noticed an unusual clustering in the direction of Hercules and Corona Borealis, indicating a massive overdensity of matter. The redshifts of these gamma-ray bursts reveal that this structure lies at a distance corresponding to roughly 10 billion light-years from Earth, meaning we are observing it as it appeared 10 billion years ago, a mere 3.8 billion years after the Big Bang. The very existence of the Hercules-Corona Borealis Great Wall poses a profound challenge to the cosmological principle, one of the foundational tenets of modern cosmology. This principle states that the universe is homogeneous and isotropic on sufficiently large scales, meaning it should look roughly the same everywhere and in all directions once you average over vast enough regions. While gravity naturally creates smaller structures like galaxies and clusters, the standard lambda CDM model of cosmology, derived from the cosmological principle and the initial quantum fluctuations after the Big Bang, struggles to explain the formation of structures this large. The expectation is that beyond a scale of roughly 1.2 billion light-years, the universe should appear smooth, with no significant overdensities or underdensities. A structure spanning 10 billion light-years fundamentally violates this expectation. It represents an extreme statistical anomaly, a lump in the cosmic fabric that is far too large to have formed naturally through gravitational amplification of the tiny random density fluctuations in the early universe, at least according to current models. The probability of such a colossal formation emerging purely by chance is astronomically low, raising uncomfortable questions. Does this mean the initial conditions of the universe were not as uniform as we thought? Or does it imply that our understanding of gravity, or even the fundamental laws governing structure formation, is incomplete on these truly gargantuan scales? While some astronomers suggest that the observed clustering might be a statistical fluke or an artifact of the observational technique, subsequent analyses using different methods have largely confirmed the presence of this immense overdensity. Other great walls have been discovered, such as the Sloan Great Wall, 1.5 billion light-years long, and the Boss Great Wall, 1 billion light-years long, but none approach the scale of the Hercules-Corona Borealis Great Wall. Its sheer magnitude sets it apart, a cosmic outlier that demands explanation. This colossal wall is not a static entity. It is a dynamic, evolving region of space-time where gravitational forces are at play across truly immense distances. Within its boundaries, countless galaxies are engaged in their own cosmic dances, forming stars, merging and evolving, all while slowly moving under the influence of the Great Wall's collective gravity and the relentless expansion of the universe. We are observing a snapshot of this immense structure from billions of years ago, a grand tapestry woven by the forces of creation and evolution. The Hercules-Corona Borealis Great Wall thus stands as a testament to the universe's capacity for unexpected grandeur, a puzzle at the very edge of our understanding that forces us to question the limits of our knowledge and the true nature of cosmic scale. It is the ultimate colossus, making our entire solar system, and indeed our entire galaxy, feel utterly insignificant. Yet it is through such magnificent discoveries that our understanding of the universe takes its most profound leaps. Our journey has climaxed with so unfathomably immense, spanning 10 billion light-years, that it strains the very fabric of our cosmological understanding. This titanic assembly of galaxies and superclusters represents the zenith of our current observations, the largest known object we have ever charted. Yet, the very act of observing it, and indeed every cosmic structure we've discussed, brings us face to face with an even more profound boundary. The limits of our perception, the edge of the observable universe, and the whispers of a cosmos that remains forever unseen. The term observable universe is often misunderstood. It does not refer to the entirety of existence, but rather to the spherical region of space from which light has had enough time to reach us since the Big Bang. Because light travels at a finite speed, we are fundamentally looking back in time when we gaze at distant objects. The Hercules-Corona Borealis Great Wall, for instance, is observed as it existed 10 billion years ago, not as it appears today. This time-travelling perspective means there's an ultimate horizon beyond which we cannot see, simply because light from those regions hasn't had the 13.8 billion years necessary to bridge the vast cosmic distances to Earth. Currently, the observable universe is estimated to have a diameter of approximately 93 billion light-years. This figure is not static. It grows slightly larger with each passing moment as light from ever more distant regions finally reaches us. However, the universe is also expanding, and this expansion isn't merely stretching the distances between galaxies, it's also accelerating, driven by dark energy. This means that some regions of the universe are receding from us faster than the speed of light, not through motion through space, but by the expansion of space itself. Consequently, light emitted from these superluminally receding regions will never reach us, regardless of how long we wait. This defines our ultimate cosmic horizon, an unbreakable barrier to observation, ensuring that a significant portion of the universe, potentially an infinite amount, will always remain beyond our ken. So, when we proclaim the Hercules-Corona Borealis Great Wall as the largest object, we must preface it with largest observable object. This crucial distinction opens a philosophical and scientific Pandora's box. What if there are even larger, more mind-bending structures beyond our cosmic horizon? What if the universe is structured on scales far grander than our 93 billion light-year window allows us to perceive? Our entire solar system, a mere 2 light-years in diameter, is a subatomic particle within the observable universe. Even the Great Wall, at 10 billion light-years, is just over 1/10 of this observed totality. But what if the true universe is a trillion, a quadrillion, or even an infinite number of times larger than what we can currently see? Cosmic inflation, a leading theory describing the universe's rapid expansion in the first fraction of a second after the Big Bang, strongly suggests that the universe extends far, far beyond our observable horizon. During inflation, space expanded exponentially, stretching tiny quantum fluctuations into macroscopic scales. This process likely inflated a tiny region of space into something unimaginably vast, creating a universe that is geometrically flat on large scales as observed, but also potentially infinite in extent. If this is true, then our observable universe, vast as it is merely an infinitesimal bubble within a much grander, unobservable cosmos. This unobservable realm could contain structures that make the Hercules-Corona Borealis Great Wall seem modest by comparison. Imagine superclusters of superclusters, or even greater walls composed of hundreds of these great walls, all existing beyond the reach of our most powerful telescopes. The question of the largest object then becomes not just an observational quest, but a theoretical one, pushing us to ponder the very nature of reality beyond empirical verification. The universe, in this context, is not just larger than we can imagine, it is larger than we can ever see. Mapping structures at these extreme distances, even within the observable universe, is a monumental technological challenge. Light from objects billions of light-years away is incredibly faint and profoundly redshifted, stretched to wavelengths far beyond the visible spectrum. This requires highly sensitive instruments, massive collecting areas, and long exposure times, operating at the very edge of what physics allows. Telescopes like the James Webb Space Telescope are designed to capture this extremely redshifted infrared light, allowing us to peer further back in time and space, revealing the early universe and the nascent structures that eventually grew into the giants we see today. Upcoming observatories, both ground-based like the Vera C. Rubin Observatory and space-based like Euclid, will continue to expand our cosmic cartography, mapping millions more galaxies and refining our understanding of the cosmic web. They will, for instance, gather more data on the distribution of gamma-ray bursts and the faint signatures of baryon acoustic oscillations, helping to confirm or challenge the statistical significance of structures like the Hercules-Corona Borealis Great Wall. However, no matter how advanced our technology becomes, the fundamental limit of the cosmic horizon, dictated by the speed of light and the accelerating expansion of space, will always remain. We are fundamentally limited to observing a sphere centered on us, a sphere that contains the light that has had time to reach us. This humbling realization forces us to accept that our understanding of the universe, and by extension, its largest objects, is inherently incomplete. We are like shipwrecked sailors on a vast, endless ocean, only able to see a small patch around our vessel, forever wondering what colossal continents or mythical beasts lie hidden beyond the horizon. The existence of a potentially infinite, unobservable universe profoundly impacts our philosophical outlook. It suggests that our quest for a definitive largest object might be an inherently futile one, bound by the physical laws that govern light and space-time. It transforms our cosmic search into an ongoing journey of discovery, where each new observation merely expands the known while simultaneously deepening the mystery of the unknown. The universe, in its ultimate form, remains an enigma, constantly whispering from beyond the edge of our vision, reminding us of the boundless grandeur and the enduring limits of our perception. Our journey has been a dizzying ascent, a relentless expansion of perspective that has systematically dismantled our intuitive understanding of large. We began with the familiar, the reassuring solidity of our Earth, then widened our gaze to encompass our Sun, a star so vast it could swallow 1,000,000 Earths. This was merely our first step. We then ventured to the realm of stellar titans, where a single hypergiant like Ui Scuti could comfortably engulf the entire orbit of Saturn, rendering our solar system an infinitesimal, fragile sphere within its bloated, incandescent embrace. From individual stars, we moved to the ethereal grandeur of nebulae, those sprawling cosmic clouds of gas and dust. The Orion Nebula, a stellar nursery stretched 24 light-years across, a distance that would contain hundreds of our solar systems, each 2 light-years wide. The Tarantula Nebula, a star-forming behemoth, spanned over 1,000 light-years, making our entire solar system seem like a single, unobservable atom within its turbulent depths. These were the true factories and graveyards of stars, galactic breath made visible, each a colossal entity in its own right. Yet, even these nebular wonders were dwarfed by the island universes that are galaxies. Our Milky Way, a majestic spiral of hundreds of billions of stars, stretches 100,000 light-years from edge to edge. To traverse it would take light 100 millennia. Our solar system, once the grand stage of our cosmic drama, became a mere dust motes in one of its spiral arms, a microscopic point within a structure 50,000 times its own diameter. From there, we soared to galaxy groups like our local group, a modest cluster of over 80 galaxies spanning 10 million light-years, then to the teeming cities of galaxy clusters, such as Virgo, which encompasses thousands of galaxies across 15 million light-years, bound by invisible dark matter. Finally, we arrived at the monumental superclusters, the vast cosmic watersheds where galaxy clusters flow together, like an astounding 520 million light-years across, and containing 100,000 galaxies, all drawn towards a great attractor. And then, at the very precipice of the observable, we encountered the Hercules-Corona Borealis Great Wall, a breathtaking, almost incomprehensible filament of galaxies and superclusters stretching an unimaginable 10 billion light-years. This single structure spans over 1/10 of the entire observable universe, reducing our Sun to an unseen flicker, our Milky Way to a lost photon, and our entire Laniakea supercluster to a mere swirling eddy in its unimaginably vast expanse. Each step on this journey has been a lesson in humility, a radical recalibration of our perception of cosmic scale, forcing us to acknowledge that the universe is not just grand, but grand beyond the most ambitious flights of human fancy. This relentless expansion of scale presents us with a profound paradox. We, as fleeting organisms on a tiny planet, are utterly insignificant in the face of such cosmic immensity. Our lives are but a microsecond, our planet a subatomic particle, our entire solar system a fleeting memory when measured against the Great Wall. Yet, it is our minds, our ingenuity, our insatiable curiosity that have allowed us to uncover these very scales. We are the conscious conduits through which the universe comes to know itself, the small, transient observers capable of comprehending the staggering, timeless grandeur that surrounds us. This unique capacity, this ability to measure, to model, to hypothesize, and to discover structures billions of light-years away, imbues our existence with a profound and perhaps unique significance. Our physical insignificance is counterbalanced by our intellectual audacity. The term largest object in the universe itself now rings with a new, subtle ambiguity. Is the Hercules-Corona Borealis Great Wall truly the largest structure that exists, or merely the largest observable structure? Our cosmic cartography, as sophisticated as it is fundamentally constrained. We are forever encased within our own observable universe, a cosmic bubble extending 93 billion light-years in diameter. Beyond this horizon lies an unobservable cosmos, possibly infinite in extent, a realm where even grander structures might exist, forever hidden from our sight. The theories of cosmic inflation suggest that the universe we can see is but a minuscule fraction of the totality, an ephemeral dewdrop in an infinite ocean. This realization morphs our quest for the largest into an enduring investigation, a perpetual frontier of both observation and theoretical speculation, reminding us that the universe holds secrets far deeper than our current instruments can probe. This grand revelation of cosmic architecture, from quantum fluctuations in the early universe to these titanic walls of galaxies, is a testament to the power of fundamental physics. Gravity, that ubiquitous yet often underestimated force, has sculpted the universe over 13.8 billion years, amplifying the tiniest primordial ripples into the magnificent cosmic web we observe. The interplay of dark matter providing the invisible scaffolding and dark energy, accelerating the expansion and stretching the voids, dictates the fate of these colossal structures. Understanding these scales is not just about appreciating size, it's about validating and refining our most fundamental theories about the origin, evolution, and destiny of the cosmos. The very anomalies, such as the statistical improbability of the Great Wall's existence within the standard lambda CDM model, serve as critical pressure points, pushing the boundaries of our knowledge and forcing physicists to consider new physics or unexpected variations in the universe's initial conditions. Each measurement, each mapping, each new detection of a structure like the Hercules-Corona Borealis Great Wall is a step closer to a complete cosmic narrative, even if that narrative constantly unveils new mysteries. The emotional impact of this journey is undeniable. It is a profound sense of awe, a humbling surrender to the incomprehensible scale of reality. Looking up at the night sky, we no longer see mere points of light, but the distant glittering cities within cosmic filaments, the faint whispers of nebulae where new suns are born, and the profound, dark silence of the voids that separate them. We understand that our existence, while physically insignificant, is emotionally and intellectually boundless, our capacity for wonder an endless wellspring. The universe is not a sterile, predictable machine. It is a dynamic, breathing, evolving entity, filled with beauty and terror, creation and destruction, all operating on scales that dwarf our very imagination. So, as we conclude this brief glimpse into the universe's most colossal objects, we are left not with definitive answers, but with deeper, more expansive questions. What lies beyond the observable horizon? Are there other great walls, other cosmic leviathans, patiently awaiting the distant light to reveal their existence? What ultimate fate awaits these vast structures as dark energy continues its relentless work? And what does it truly mean for us, these conscious specks of stardust, to exist in a universe of such staggering, unimaginable proportions? We may never grasp the absolute totality, but the journey of discovery, the continuous stretching of our minds to encompass these cosmic truths, is perhaps the greatest adventure of all. The universe remains an infinite puzzle, and we, the curious Terrans, are its eternal, eager investigators, forever charting the borders of imagination.